Today, I want to talk to you about global wind patterns. And this has a lot to do with uh, where pollutants in one part of the planet are likely to end up, how severe weather will be distributed across the planet. And it just affects a lot of the environment on planet Earth, both naturally and from man made causes. So let's get on it. So, as we said earlier, convection occurs anytime the radiation from the sun, light from the sun, interacts with our surface. It gets absorbed. It causes the Earth's surface to become hot. The air immediately near the surface heats up, and as it does, it becomes less dense and it rises up. It cools and it sinks. And remember, as it rises up, the moisture it carries tends to condense and cause precipitation. It's also worth noting in this particular graphic, we see that it releases what's known as latent heat. If you recall from chemistry, it takes quite a bit of energy to cause water to go into a vapor state, and that energy comes back to you when it goes into a liquid state. So as this moisture goes up, it releases more energy into the cloud, which is going to be important when we talk about hurricanes later. Okay, now it's hot at the equator, as we've said earlier, because the sun's rays are more direct here. They're more concentrated. So there's more light energy per square meter at the equator than there is at the pole where it's spread out. Now, we'll just assume that the North Pole is at a right angle to the sun's rays for right now. If the world didn't spin, if the world didn't have continents, here's basically what would happen. Hot air would rise at the equator where it's warm. It would drift northwards. It would sink at the pole where it's cold. And the surface winds on planet Earth would always be blowing from north to south. So we would say there's always what we call a north wind. I know it's kind of annoying, but winds are named for the direction from which they come, not in the direction that they're going to. So think about it. If you face into the wind, the direction you're facing, that's the name of the wind. So the north wind is the wind coming out of the north. That's all there would be. Now remember, rising air makes low pressure and sinking air makes high pressure. And air, like and any kind of fluid, is always going to be pushed from high pressure to low pressure. So that's what we get, excuse me, if the world didn't spin. But it does spin, and that's going to make some complexities. Because it spins, and we'll get into this in a little bit, it tends to break up those single cells into three smaller cells. These cells are known as the Hadley cell, the Ferrel cell, and the polar cell. And basically, let's think about it. Well, anyway, so right now, I guess for this slide, what I just got to point out is it's broken up fairly evenly in terms of latitude. So at 0 degrees, it rises and then it sinks at 30 degrees. In the Ferrel cell, it rises at 60 degrees and sinks at 30. And then in the polar cell, it rises at 60 and sinks at 90. So it's pretty easy to remember 30 degrees. We have 90 degrees from the equator to the pole. And thank goodness it's evenly divided between those. Now they're named the Hadley, the Ferrel, and the polar. And we'll get to that in just a minute. Okay, like now. Okay, so the Hadley cell, Hadley's the guy who first came up with this idea. We thought it would go from the equator to the pole. The Hadley cell circulates between the equator and 30 degrees north or south of the equator. It tends to be the most consistent and strong of the cells because equatorial heating is so pronounced. So warm air rises at the equator and it sinks at 30 degrees. Now, I'll tell you, the easiest way to remember this is then to go to the pole. At the pole, it's cold here, so we'd expect cold air to sink. It goes about 30 degrees, warms up, and rises. So we get the polar cell going like this. So surface winds at the pole are flowing from north to south. Surface winds in the Hadley cell are also flowing from north to south, generally speaking. The Ferrel cell is kind of caught in between. And so the way I remember it is the Hadley cell is sinking at 30 degrees, and so is the Ferrel. The polar cell is rising at 60, and so is the Ferrel. So it's kind of like it's caught in between these two conveyor belts. All right? But that means the surface air between 30 degrees and 60 degrees is actually traveling away from the equator in a northward direction in this hemisphere and a southward direction in the other hemisphere. Let's recall that rising air is associated with low pressure and precipitation. And so what we find then is at the equator, there's a lot of rising air. So at the equator, we have low pressure and lots of precipitation. This is why we have tropical rainforests. This convection forces water to precipitate, and that's what allows these wonderful forests to exist. Now, 30 degrees away from now it lifts the air up, it loses its water, it gets to the top of the troposphere, and then it sinks back down around 30 degrees. And these are rough numbers. It's not always exactly 30, right? But what happens is as it sinks back down, this has no more moisture in it. And as it sinks down, it warms up and allows it to grab even more moisture. So basically, we have dry air sinking at 30 degrees. Now remember, sinking air makes for high pressure, and it tends to be very dry. So we find that as most of the world's deserts, the major deserts like the Sahara Desert and the Sonoran Desert, and so on, they tend to be found around 30 degrees north or south of the equator. Australia, about 30 degrees south of the equator. And also, too, it sinks at the poles. Now, you can't have an equator you can't have a desert if you don't have land, but there is land in the southern hemisphere at the pole. And it turns out the South Pole is a desert. It's the driest desert on the planet. It just happens to be covered with water, which oddly enough, because once in a while it does snow, but we have descending air that's very cold and very dry. And so we have high pressures at 30 degrees, and we have it at 90 degrees. Let's see. We also get, and it's worth noting that we also get rainy conditions associated with areas around 60 degrees north or south of the equator. We tend to have this unsettled, wet weather, but it's not quite as pronounced as it is at the equator because we don't have quite that strong of heating to cause the uplift. All right, so just to reiterate, the precipitation is high near the equator because we have warm air rising and then condensing and dropping its moisture as it moves upwards. We have deserts at 30 degrees north and south of the equator because we have dry air descending after it lost its moisture on the way up at the equator. And that's going to be important when we look at the distribution of biomes in the world. A lot of it has to do with the movement of these cells and how they cause rain to fall or not fall. Now, all right, you ready? Here we go for the weird stuff. Because the world is spinning, as these winds try to make their way across the surface of the Earth, they get deflected, what appears to us to be deflected, either to the east or the west. And this really is called the Coriolis Effect. I'm sure you've heard of it. And I'm going to try to help you understand why it occurs. And don't get too caught up in it. I'm not going to really try to hammer you on this, but I do want you to have some general understanding of what causes it to happen. Now, it really comes down to this. Sorry, it's late. I'm tired. Oh, but I've got to get this done, right? So, if you were standing at the equator, given the circumference of the world, it's about 25,000 miles around. It makes the trip in about 24 hours. So at the equator, you're traveling about a little over 1,000 miles per hour or 1,650 kilometers an hour. You're booking, right? But if you're standing at the equator with Santa Claus, you don't go anywhere. You just stand where you are and you just go around like a shawarma on a steak, if you know what that is. Oh, shawarma is so good. All right, but you're going 0 kilometers an hour. The point is, the closer to the pole you are, the slower the air is moving. The closer to the equator, the faster air is moving. Well, what does this cause to happen? I'm so tired. Okay, so I'm going to use the fast car, slow car analogy. Hopefully that will help you get the idea. So imagine if I'm trying to throw a watermelon between two cars. I'm trying to throw a watermelon from this car to this car. Now here, these two cars are traveling at the same speed. Here I've got a slow car farther from the equator, and here I have a fast car at the equator. So here we go. You ready? All right, this is my awesome graphics, my Eric Sampson's computer graphics at work. Okay, these two cars are traveling the same speed. If I try to throw a watermelon, I throw it this way, but it's still moving this way because the car was moving that way. So what happens is, a second later, the two cars are still side by side because they're traveling the same speed, and the watermelon is just moving between them. And it'll make it straight to their car, and if I was to draw a line showing the way this person sees the path of that watermelon, he would see it going this way. But what if the cars are traveling at different speeds? And this is hard. It really is a hard concept because it has to do with reference frames. And reference frames are always hard for people to get a handle on. But let's just say, If the world didn't spin, then the air at 30 degrees would be moving the same speed as the air at the equator, 0 kilometers an hour. And so, as air tried to move from 30 degrees to the equator, which it does, it tries to move southward because 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 the Hadley cell is doing this, right? It would just move in a straight line, but that's not what happens. If you try to throw a watermelon from a slow car to a fast car, it looks something like this. When you first do it, the two cars are side by side. But what's going to happen? A moment later, the slow car has traveled a little bit this way, but that fast car has traveled faster. And it's now here. It's no longer exactly side by side with the slow car. And that watermelon, which is moving straight away from the slow car, it's now behind this car. So if you were in this car, you would see that watermelon going like this. So now let's look at the world. That's what we see the winds doing between 30 degrees and 0 degrees. They're trying to move from slow to fast, but let's just say I have a person here and a person here, and I'm trying to throw air between them. Just like that watermelon, the air is going to end up coming in behind the fast-moving person because that person moves this way, and so as the air goes straight, it seems to have this bend to it. So this basically sets up these global wind patterns. So what we find is between 30 degrees and 0 degrees, the winds tend to have this movement from northeast to southwest, and we call these the trade winds. So basically what happens is, the best way to think of this is this way. Because of these speed differences, anytime air is moving towards the equator, it's going to get apparently deflected to the west, regardless of which side of it you're on. As it moves from the slow regions to the fast regions, it's going to get deflected westward. All right? Same thing happens up here at the poles, although it's hard to see. It's less pronounced up here, but the same thing. Air is trying to move from the surface, is trying to move from north to south. And if air is moving towards the equator, it's going to deflect to the west. All right? Now, unfortunately, we call these winds the polar easterlies because they blow out of the east as they move to the west. It's so crazy. Now, all right? And then in the Ferrel cell here, it's the one part of the planet where air is moving northwards, away from the equator. So instead of being deflected to the west, it's deflected to the east, making winds we call the westerlies. Okay, so here we are. Let's just walk you through the different wind systems. The trade winds are biggies. So the trade winds are these very consistently blowing winds that blow basically in a westward direction in a region between, say, 30 degrees and close to the equator. All right, now remember, at the equator, at 30 degrees, there's not a lot of movement, but in between there is, and it tends to take this pattern. And these are very strong winds. They're very reliable. This is what the sailors used to use to get across the oceans because they're so consistent because of the strong circulation caused by the powerful convection of the sun's rays hitting at the equator. They call them the trade winds because they help people in their trade of moving spices around the world. And unfortunately, other things too, like slaves. Now, the prevailing westerlies come out of the west. That means they're blowing to the east. Those are the ones that exist between 30 degrees and 60 degrees in this Ferrel cell, which is doing this. And the surface winds are trying to move northwards, but they'll deflect to the east. So if you were standing here, the wind would be in your face. We call these the prevailing westerlies. So when people sailed across the ocean, what they would do is they used to sail down we're looking at the Pacific here, but let's just say it was the Atlantic. People would sail southwards from Europe until they got into the trade winds. The trade winds would carry them across the Americas. Then they'd work their way up the Americas until they got into the westerlies, and the westerlies would blow them back across the ocean. So they took advantage of these two wind systems in order to do that. Then we have the polar easterlies, which blow to the west as the wind tries to move this way. And the polar, I guess it matters to be up there, but honestly, there's not many people up there, so we're not going to concern ourselves with it too much. We mostly concern ourselves with the westerlies and the trade winds because the vast, vast, vast majority of humanity lives between 0 and 60 degrees. Now, the boundaries between these areas are areas where there's not a lot of surface winds. So this is especially pronounced here at the equator where we just have air rising upwards, so there's not any prevailing winds. If you remember on that assignment you just did, that had the rain shadows. There weren't any rain shadows in Ecuador, and that's because Ecuador's at the equator, and at the equator there really isn't much wind. So we call this area the equatorial doldrums. Then we also have another area like this here at 30 degrees where we have the descending air, and there's really not much wind here either. They call these the horse latitudes, and there's some debate. Is it because they ate their horses because they couldn't move their boats? Or I've heard a number of things about that, but basically somehow sailors with horses named these things the horse latitudes because they got stuck there. Okay, the last thing. I'm sorry this is going on so long. The last thing is this. In moving air around the planet, because remember, when we move air, we're moving energy, we're moving atmospheric pollutants, we're moving water that's used for biomes. It's a big deal. Well, there's also this thing called the jet stream. Now, so the jet streams are these high altitude wind systems. They're not surface winds, they're upper air winds. In fact, they discovered these during World War II. The United States built a special pressurized high altitude bomber. I forget what it was called, but basically it was able to drop bombs. They were trying to drop bombs on Japan from very, very high up where they didn't have to worry about enemy fighters couldn't go that high. But they always missed their target. They could never hit their target. And they eventually realized that their bombs are being deflected by these high altitude winds they didn't know existed. So these high altitude winds are known as the jet streams. There's two sets of them in either hemisphere, one that's around 30 degrees and one that's around 60 degrees, where the two cells meet. So basically, between the Hadley and the ferrule cell, between the ferrule and the polar cell. And in these regions, the winds can blow pretty fast. They blow from 150 kilometers an hour to 400 kilometers an hour. But the general motion, always because of the rotation of the Earth, is in easterly fashion. Now, the greater the temperature difference between the two sides of these cells, so like this is the what do we have here? Here we've got the Hadley cell, and here we've got the ferrule cell. We've got a temperature difference between them. The greater the temperature difference between them, the more pressure difference there is, and the faster these winds blow. And what happens is they're near the top of the troposphere, kind of near the bottom of the stratosphere. And commercial jets fly that high. So what they do is if they're flying in an eastward fashion, they'll just get up in there and get carried along. And they'll get to their destinations much faster than they would otherwise. They try to avoid them when they're flying the other way because they just are basically, it's like a swimmer trying to swim against a strong current. And the other thing is that jet streams, they're not just straight east-west. Like they're moved by high-pressure and low-pressure systems on the Earth's surface. And that tends to deflect these streams. They tend to have this sort of sinusoidal serpentine fashion that's constantly undulating like a snake. And what happens is a weather system will be trapped here, and as this thing moves like a snake, it will push these weather systems to different parts of the planet's surface. So that's an important factor in determining how weather is going to play out, or whether a heat wave is going to be extended, or so on. So atmospheric scientists are very interested in trying to monitor these rapidly changing undulations of these jet streams. Now, there's a couple of great videos you ought to watch on these topics. I would encourage you to go to the slide presentation on this and click on these and take a look at them. Sorry to make this so long, guys, but thanks for watching.